Reaction rate calculations. We can see here we have some figures for a volume of gas against time reaction. The starts at 0 and the time's going up in 10 seconds. The volume of gas being produced every 10 seconds is given. Okay. The equation that is used for reaction rate is in the front of your data book, and it is reaction rate equals change in product divided by change in time. It's often written as delta P divided by delta T. If the question asks find the reaction rate for the first 30 seconds, then we would first off write the formula. Reaction rate equals change in product divided by change in time. Then we will put in what the change in product is. Between 0 and 30 seconds, we are making 42 centimetre cubed. So we'll have 42. And the change in time is between 0 and 30 seconds. Is going to be 30. So 42 divided by 30. This is going to equal 1.4. And it's in volume per time. So that'll be centimetre cubed per second to the -1. I still prefer the old method, but that's what we should be using. Okay. If we're asked to find the reaction rate between 2 points that are given as far as the time's concerned, then we do it exactly the same way, but we're just using the amount that's been made between those 2 points. So in this case, we still write the formula. Reaction rate equals change in product divided by change in time. We would then put in what our change is. So the change in time would be 40 seconds minus 20 seconds, which is going to equal 20. The change in product would be what we've made at 40, which in this case is 52, minus what we've made at 20, in this case is 20 is 30. So we would have 22. This would give us a reaction rate of 1.1. Again, centimetre cubed per second minus 1. You will be expected to be able to draw a graph, possibly 2. And the idea is that the thing you are in control of, in this case you are taking the time, so you're in control of the time, will go on the bottom. That's our independent variable. You must put in the full wording, you must put in the units. The things you are control that's been measured because of you measuring the time goes up the side, the y-axis. And again, you must put all the wording in correctly and with the units. That would be volume of gas, again centimetre cubed. That automatically gains you 1 mark. A second mark is gained for correctly putting the scales on. The graph paper will be of an appropriate size. So we've got the scale here as 0 to 60 for the time. That will be the first one to go on. And remember, this is a numerical scale, so it has to be properly spaced out. So we have 10, 20, 30, 40, 50, 60. Okay. And going up the side, we take the bottom number, which is 0, and the top number, which is 55. And again, we want it as large as possible, but it's a numerical scale, so it has to be properly spaced out. So we'd be, in this case, look at again 0 to 60. That would fit it on. Okay. The plot is as you would always do, these are coordinates. So you follow the bottom line up, start with the 10, and where that intersects with the line from the y-axis for the 15. So we'd follow that up, follow the 15 across, and that would be our plot. Same for the 20 with the 30 across. So we'd follow the 20 line up till it intersected with the 30. Right, for the 30 line with 42, same idea. For the 40 line it's 52. For the 50 line it's 55. And for the 60 line it's also 55. That will give us a graph. It is not a graph that you've got to play dot to dot with. It is a simple enough graph just to try and draw a freehand curve through the points. The points need to be within half a square of the correct answer, and your line, once it needs to be freehand, that's 2 extra marks. Okay. Using the graph to find the reaction rate is a similar idea as to the using the actual figures, but you need to put lines on the graph. If we wanted to find the reaction rate at 10 seconds, we would draw a line up at 10. We would then draw the line across to find out where it would be there. That would be our delta T. That would be our delta P. And I accept the numbers are pretty easy in this. So we'd have a reaction rate of delta P divided by delta T. In this case it would be 15 divided by 10 equal 1.5 centimetre cubed per second minus 1. If we wanted to find the reaction rate between 30 and 40 seconds, we do exactly the same. Line up at 30, line up at 40. That is our delta T. Follow the lines across. 30 is 42, 40 is 52. That is our delta P. So the reaction rate would be delta P divided by delta T would be 40 minus 30 would be 10. At the top at 40 it's 52. At 30 it's 42. That would be 10. So therefore we'll have 1 centimetre cubed per second minus 1. The line A, the black line, indicates the normal graph. The line B, the red line, graph with a reaction rate increased, i.e. temperature increase, concentration increase, use of a catalyst, surface area increase. The line C, purple, is graph where the reaction rate has decreased, i.e. gone the other way, smaller surface area, lower temperature, no catalyst, that sort of idea, lower concentration. And the line D, that is where only half of one of the reactants are used. This shows that we're only going to make half as much of the product. The X's indicate where the reaction's finished. It does not finish at the end of the line, it finishes when the line goes flat. If you notice, A, B and C all make the same amount of material as well. It's just the speed that the material is made at where we get a difference.